Good afternoon. Sorry, good afternoon, everyone. Let's start the course. Let me see. Hi, good evening. Okay, let me first share my screen share. And then let me have my annotate here. Okay, so in the last lecture, let me see word time. I believe in the last lecture we finished. Yes, we finished here. I remember I mentioned how to push those kind of contours into the door. Sorry, into the wall. I believe it's here. Okay, here we go. So we can push all these contours here. Let me run it. We can push all those contour things. Oops. We can push all those contour things onto the plane of the X, Y, and the Z, and then be careful. The trick is the offset. I remember I set up something that if the offset is the same, but we set up the Z limb to be another number, then it's gonna be completely different. Okay, make sure these things, that they fit each other. Let's continue the thing. So okay, the next thing is the 3D plots. By comparison with the 2D plot, somewhat the 3D plot is easy because you don't have to have figure into that, and then axis 0, 1, 0, 2, something like this. Everything's just gonna be very direct. To save my time, let me first create one here. Let's say 3D subplots. Okay, I believe most codes are the same. Let me see, what did I plot here? It is a scatter surface and contour. Okay, so let me just copy and paste everything from here, and I can just make something, change something. So first of all, important NumPy this I need a theta to have parametric equations, and I have this. I have the parametric equation of the mesh grid here. Okay, here we go. So now here we want to kind of like create a 3D subplots, right? Okay. Excuse me. And excuse me. So here, it's just a one plot. So you may think that, well, it's simple. So let me first let me say this is the 3D contour ball. Okay, you may think that, okay, I just have a firm for a contour ball so that I can have, let's say, okay, assume I do not, because this is gonna be one of the tricks, but assume I don't have this. Okay, so I write like this way. So XYZ, instead of have the contour, we can have what to remember. We can have scatter. And then have the scatter, I can have I don't have the density here. And then I can have another thing is I forgot again. Scatter. Oh, so surface. Let me change 3D scatter ball, scatter, and then surface ball, surface. And then I say, okay, I have the plot surface. Plot surface. Okay, so I believe I can run like this way, right? Okay. Guess what's gonna happen if you run it? Let's go. Let's see. Sorry, let me close this one. Otherwise, it's gonna be very slow. Okay, let's run it. We're gonna something interesting. What? Three figures? Why? That's the trick why I have the 1, 2, 3. Remember, I just removed the 3 here because for Python, you tell me plot this, plot this, plot this. Yes, you did say it's add a subplot, but looks like they're all independent. You know what I mean? For Python, it doesn't know that you want to make all the things in one plot. So how to make it know? I'm not sure whether if you make it like this way, I'm not sure whether it works. Let me see. I'm just curious. No, it doesn't work. No, it's gonna be kind of like everything gonna be in one still, but and it will cover over kind of like cover the previous one. It's gonna be kind of like overlap. Let me show it again. I'll close it shortly. You will see a big mess. Everything's there. Why? Because everything's kind of like gonna be. Let me see. No, it's gonna be overwrite instead of like overlap. It's gonna be overwrite because this will be last one. So we basically the trick here. So what we're gonna do is that we will have figure equal to plt dot figure. So we will use this. And then you see, since the figure already equal to PLT the figure, so here I don't need a PLT figure again, I can just use a fig. So this tells Python that, hey, we're doing everything in one first. And then another thing is, remember here, I need to add something, which is, I know it's 2 by 2 by 2 by 2, although we have only 3, right? So this is gonna be 2, 2, 1. This is gonna be 2, 2, 2. And this is gonna be 2, 2, 3. So this tells Python, hey, you're gonna really do this, and this is the first one, second one, third one, and again, the first one means the up left one, the second one means the up right one, the third one means the down left one. Okay, let's see. So we should have, here we go. So we have everything here. We have, and you can see actually in each subplot, it has an independent GUI, so that you can just do this. Okay, so and then 3D scatter, 3D surface, 3D subcontour. So this is the thing. Somewhat I feel this is even easier than the 2D plot actually. And the one good thing for PyCharm is that it shows you relatively good, this kind of like a hint. For Jupyter notebook, it doesn't have very clear, at least for me, in many cases, you have to wait for a long time, so that's the thing. Let me see here, subcontour. Okay, so here we've already shown everything about 3D. One of the most important thing is the mesh grid. This is the same as the linear space for 2D. Okay, we mentioned, let me see, scatter. Let me see, we mentioned the lines, scatter, some basic things, plus mesh grid, yes, and then surface and then contour. And then some tricks here, push the things, the contour lines onto the wall, and then subplots. Okay, next, go back to the main topic, which is linear regression. So remember, lecture number 4 is called the linear regression 1, if I remember correctly. Lecture 4, yeah, linear regression 1, that is. And then this is data visualization, and then lecture 6 is gonna be linear regression 2. But we're still, in under the linear regression. So I have this data. This is the 3D data. Let's see how can we plot the 3D data here. So to save my time, I'm gonna wait, let me first open the Jupyter notebook. To save my time, I'm gonna directly cheat from lecture 5, because I remember in lecture 5 I wrote a class already. So that's another advantage of using class. You can save your time. Okay, let me first create number 6. Where is the name? Okay, lecture 6. Data visualization by Matplotlib. Oh no, sorry. Wait a minute. Sorry about it. Wait. It is no. We are in lecture 5. Sorry, not lecture 6. So in other words, I already have this. Yes. I can directly borrow the cell here. Sorry about it. Let me close this one. Believe I don't need it, so I can keep working here. Let me see. My last code was here. Yeah, my last code was here. So in this code, basically we wrote it, we pack it in the class. We have initialization, we have the plotting, which is a 2D here. So basically what I do is I plot the training data, I plot the test data, and then I plot the prediction function, the predicted function. Here it is aligned because it's 2D. So I remember I got a typo. Let me see where it was. I remember last time after the class, I fixed something. Okay, here we go. If you go back to the video in the last class, I forgot to put a self here, and then it shows what is data. It asks me kind of to define data, and the truth is because here I already defined self.data, so you need to add the self.data. I feel this is I believe this is two typos. Another small change I believe was here. Let me show. Why don't it show the line numbers? Another thing is here, which is line 30. So I remember last time I forgot to put this and make the Y prediction very long. So that's the same. But this is really not big deal. I mean, this is because this will show the error. Okay, so now I'm gonna copy and paste here, press escape, and then press B. So when I press escape, it's gonna be in a command mode, and then press B. It's gonna, come here. Okay, now paste. I paste everything here. And then let's see what I need to do. Do I need to add any libraries here? Second learn, everything's here. Okay, looks good. Everything's here. And then we can keep all the initialization function the same, but we do need to change this one. Let me call it 3D plot. By the way, if you want to, you can just simply make a plot fitting, so we can determine if x, self dot x dot shape 0, which means the dimensions of x, fx equals to 2, then go this one. If it's a 3, then run the thing that we're gonna go. Then it's 3, then do the thing we're gonna do here. Otherwise, which is else, print cannot plot, But anyway, here to save, it's just super simple. Here to save the time, I'm not gonna do it here. So we're gonna do something similar to this example, which is I wanna plot the training data, the test data, and then the predicted plane. Be careful, it's no longer the line, it's gonna be the plane. Why? Because now we're gonna play the 3D data instead of the 2D data. By the way, let me show you the data first. Okay, so the 3D data, here we go. So we should have a y, and then anyway, we should have a y, and then we will have an x and the x1 and x2, and hence a 3D. Y is a one dimension. Okay, now let's go. I believe I can close it. I don't think I will need it anymore in my class, this class. Okay, and then and then we will have first of all, let me make this one. I believe it's a 3D. And then you can have let me see. Okay, first of all, is here I need to change it to be x equal to plot dot figure dot add subplot. Okay, now it's going to be projection equal to 3D. Okay, now I tell Python that this is 3D. Okay, now I just simply need to make those things to be AX. And wait, am I trying? Oh, okay. Here, be very careful, because here, this you don't have the Y train. The second one should not be the Y train. Your Y axis, the thing should be X train. The first column, and this one should be X train, the zeroth column, and your Z actually equals to the Y train. Be careful. This is the Z. So I should have the self X train. Then how can I make it a zeroth column? It's gonna be like this way. So I'm gonna have, remember when we mentioned the job, we can have this self dot X dot column 0. So this tells me, hey, what is the column 0? Of course, for here, because you can see the data, you can say it is just x1. Yes, you can do it. But I would say this is a more, general method. Okay, and then, okay, so this is, give me 1 second. So this is self.x train self column 0, column 1, yes. And then similar here, the only thing I need to do is to change the column, the train to be test. So X train, not X train column. Here's X train column as well. Let me use this one to split it into 2 lines. Okay, now here similar cells dot X test column 0. Column 1. So the Y, okay, I can keep this as well. And then what I'm gonna do is I'm gonna okay, so here I need to already plotted the training test data and training data, then to generate the things. So okay, here in the 2D, what we did is we have the line space, right? But here we cannot have the linear space anymore. Although we will need a linear space to generate what? To generate the the points, and then we can use the match grid. So here, oh, okay, let me forget about this. It's just pretty troublesome. Let me simply just use AB, make my life easy. Okay, so I have this one, and then here it's not self x min anymore because my x has 2 dimensions, so it should be self min 0, self max 0 as well. Okay, so this is to generate, the XY plane, which is the X1, X2 plane. Here, it's gonna be from the minimum of X0, I mean, the first dimension, and the maximum of the X, first dimension. And now I can do the same thing here. The only thing I have to change is to make, this 0 to be 1, meaning the first dimension, and because X is 2D again. Okay, so here's the first dimension, and now I can just do AB equal to MP dot mash grid. Come on, it doesn't give me any hint anyway. Mash grid and then AB. That's why sometimes you use a PyCharm and write code is really much faster. Okay, and then and then let me put a Z here. Z equals to self dot intercept plus self dot model. No, because here I do have beta 1 and beta 0, remember it? So if I put a 0, this means beta 1. Be careful, okay? The real beta 0 is model dot intercept. So this coefficient 0 means beta 1 times, here I change the name to A plus beta 2 dot model dot beta 2 times B. And hence I have the Z function. And now I can just, I can just do this. X equal X dot plot. And here I'm not gonna have this anymore. I'm gonna simply have A, B, and Z. And then I'm gonna have, let's say, let me use color equal to red. Did I use red color? Sorry about it. Let me cheat a little bit. Yes. I even have an alpha here. Okay. Color equal to red. Color equal to red. Line width, I don't need it anymore. I have an alpha equal to, alpha is to make it transparent so that, I can see something. And then I'm going to change it from the predicted line to be the predicted plane. And now I will have x dot, be careful, usually when you use x set x label, set y label instead of just, kind of like dot y label. That's the thing. X dot, it must because, different people code it, that's why. And then final x dot set z label z. And then we will have, and I remember I called y, I remember. Give me 1 second. Z or y, where it is. Okay, here, it's y. Okay, and then the training data, the test data and the predicted plane. X dot set type level. X dot legend. Okay, PLT dot show is still the same thing. PLT dot show. Okay, now instead of LR1, let me call it LR3. Here's not plot fitting, it's plot fitting 3D. Okay, now let's run it. There we go. Something wrong again. Spell wrong. Column. Wait. Let me see. COL. Columns. Sorry, it should be columns. Let me see here. Yeah, let me see. Still wrong. Data frame. I changed columns already. Let me see what is wrong. Then have column, which line? 56, and then columns. Yes, I made it to columns. Why I already changed it to columns? Self.x train dot columns. Let me see what is wrong. That's interesting. Looks like the same thing here. X train dot Let me see. Self dot x train dot columns 0. Did I miss any parentheses? Oh, here. Sorry. That's why I really always want press the table, the tab a key so that it will avoid it. But unfortunately, in terms of this, it's not as good as what still wrong. Not as good as PyCharm. Blah blah column cannot be broadcast with remap. That seems that something about the shape is wrong. Test. Let me see. Do I have any issues here for the shapes? Hmm, that's interesting. It doesn't have the things test data. Wait a minute. Looks like the something that the test thing is wrong. Let me see here. Self test columns, the columns 0, 1, the test data. Wait, why it plot this one correctly, but I cannot plot the y x test. Let me see why it is wrong here. X test dot columns 0, self dot x test dot self dot x test columns 1, y test. And that's interesting. I temporarily cannot find the issue here. Let me temporarily let me see whether I can at least whether I can at least plot the plane here. Equals to uh that's something weird. Okay, I will have to open my cheat sheet since I cannot find it. So let me directly compare the code here because I clearly remember I ran everything correctly. I don't know why. That's interesting. Let me see. Plus 3 is here. I can make it bigger. Figure at the plus 3, yes, and then X train self X train 0 X train B Y train Y test column 0 S test columns 1 and let me see Y test label equal to this is not a big deal. I can use whatever the color line space here X min X1 measure is equal self model intercept here A and model here B, and then color equals to red alpha label. That's interesting. Let me see 3D alpha. Oh, wait. Test size. No, it doesn't matter. It should be the same thing because here I already put only 2 parameters. Test size equal to self dot test size. Yes, this is not a big deal. And then L3 dot plot fitting 3D. Why it shows the error? That's interesting. Oh, well, that's Okay, I know why. Sorry about it. I know why. Uh, see, wait. This is the reason. Yes. Okay, now I should give me a second, self dot this one, and then minus this one, then move this one, and then if I have this, let me see. Interesting. 46 x plot. Wait. Sorry, my fault. It's not plot. It should be plot surface. Yes, so in this case, yeah, but because remember before we mentioned the plot cannot accept the 2D data, while scatters can, but plot cannot. Here A, B, C, these things are kind of a two-dimensional data. Hope everything's correct now. Okay, great. Okay, wait. Let me do one more thing, which is to Matplotlib PT so that it will put the pictures outside. Here we go. Oh, finally. Okay, so this is the data that we have. So again, let me make it to be black. I feel black is better. I don't want where it is. Here, let me use the black one. Okay, here we go. Okay, here we go. Maybe the yellow is better, whatever. So the blue color are the training data. The black triangle is the test data, and this plane is the predicted plane. And you can easily see kind of like, well, this prediction, initial visual, I feel it's not too bad. Let me see what is R score here. R score is 87%. Usually if R score is more than I square the score is more than a point 0.81, it's considered to be good because square root of that is already 90%. So that's everything. Sorry for making the mistakes. And actually, you know what? Those things, if you directly if we can better the hint, not the hint, the table key, it will be actually better. Yeah. Okay, so that's everything about lecture 5. So in lecture 5, we showed the basic ways of using Matplotlib to do the data visualization. So here we can only do 2D and 3D due to the limit of the physical world we're living. I hope I can plot the 4D, but okay, and also show the examples how to do these things for the 2D and 3D linear regression. Next, let's go to lecture number 6. For lecture number 6, it is linear regression 2. So we've already learned linear regression 1. Let me review this part again because this is really extremely important. Okay. First of all, let me first of all review this one, and then I will go back to slide number 2. Let me first go to slide number 3 first. So least square linear regression, what do we need to do? Suppose we've seen those kind of points, right? What we define is first we want to find a line, or let's say find a linear function which is closest to all the point, summation of the points. But what does closest mean? I remember we showed basically we want to calculate the square of the summation of the square of this distance. Why do we need to do the square? Because it's difficult to use absolute value in optimization, right? Why do we need to do the summation? Because we have so many points. Unless you have a weight. I mean, by the way, you do have a weight option if you want. You can say, for example, I just love this point. I set this point the weight to be 2 or others to be 1. Technically, yes, that's okay. But in most cases, if we don't have a bias on any point, so we assume all the points weight is 1. And hence, we just simply summation the squares of all these, the distance. And then to make the least square, what do? We will choose a beta, which let me zoom. Let me see how can I here. Okay, we'll choose a beta which makes, let me make it a box here, make this one the minimized, right? So that's the point. So the notation here, the notation here, arg main beta, that means arg means the argument. That means, hey, tell me which beta is gonna make this thing minimized, and I will take this beta to be on beta head, meaning that, okay, I will choose this beta. So that is the overall point. And also by very simple mathematics, we can get to the solution OLS, the ordinary least square estimator solution, which is this, which is basically nothing, just make the derivative and make the what to be zero because it's a quadratic. Use the matrix form is quadratic. Make the nabla to be zero, which is a gradient, and then here we go. You can get a point. So this is the meaning. Okay, now let's go back to the overfitting. So everything looks very good, right? So why do I need to learn linear regression too? What's the point? Well, the point is basically on the concept of overfitting and the concept of data dimensional reduction. So first of all, let's see what is the overfitting. So overfitting model is something which is overtrained on a particular data set, such that the noises are like they're kind of like fit too well, you know. So here what I mentioned is it's kind of like typically an overfitting model works almost perfectly on the training data itself. And if we stop here, you might say, hey, isn't it good? I mean, what's perfectly wrong? I mean, everybody likes something to be perfect, right? What's wrong? The problem is here, but it will not, predict well on new data which is not included in the training set. In other words, you're only good for that specific training data set. But that's not the point because the training data set I've already observed there in the past. What I want to do is for a future data that I've never seen, I want you to do the prediction, which is, I give you the x, you substitute this x into your f function, and then you give me a y. That's the reason I want your future data to run, well, if possible, perfectly, right? Instead of training data. So let me first give you an example, a visualized example. So consider the points. My original points are like this. Can I just fit like this way? And you see, look at this. I fit like this, so it's a perfect fit, isn't it? I mean, every point exactly follows on my function. Isn't it a perfect fit? I mean, your R squared is gonna be one, strictly one. Everything is perfect, but we don't like it. You know why? Simply because here, to be honest, I cheated because here I have 1, 2, 3, 4, 5, 6, 7, 8. I have total 8 points, right? And you know how did I get this function? I did this function by fitting 8 data. I'm using 8 data to fit a 7th degree polynomial. In other words, I set up to be y equal to beta 0 plus beta 1, x plus beta 2, x beta 2x cubic blah blah to the beta 7 x to the power of 7. That's a 7th degree polynomial. And look at here how many variables I have, parameters I have. Beta 0, beta 1 till beta 7. In other words, I total have 8 parameters and I have 8 data. That means what? That means I'm gonna solve 8 variables by 8 functions. So of course you make this one, it's gonna be a perfect fit. In general, if you have n data and you use n minus 1 degree polynomial, so you will always get a perfect fit. But is it what we really like? No, it's not. Why? Because actually, I want to say this is a good fit. It's something like this. For example, the next point, it's very possible to be, something like this, right? Would be very possible to be something like here. But think about it. If you just, let me just plot it. If you let me see, plot red color. Give me the red color. Okay. So if you write wait. Let me use another color. Let me use, let's say, the green color. And then pen. I need a pen. Okay. So, and then if you fit, something like this way, you will be like this way. You know what I mean? You will be up, and you will no longer be able to touch, those kind of points here. That's why this is not a good fit. It's an overfitting. Again, meaning that it works perfectly on the specific training data itself, but will not predict well on a new data. So this is overfitting, and this is underfitting. I mean, underfitting is very clear. Say, the trend should be something should. Sorry. I can also draw a line. Let me directly a straight line. Okay, something should be like this one, and you give me a red line like this. Of course, that's the fitting result is very bad. Your R square going to be super low, and of course this is underfitting. And what we need as a fitting in practice is something like this way. This one. This one is a good fitting, meaning that it works not too bad on my training data and it will work well in my future data. And this is, the practical one, the thing that I want. So this is the overfitting. This is issue number one. And issue number two is this. So when we are doing the OLS estimator, remember we have this XTX inverse. And I remember I mentioned that we assume this one is invertible. But what if it's not invertible? Or let me give you a very simple example, which is, what if n is less than p minus 1? Or n is less than p? Remember, what does n mean? N means how many data I see it. P means how many dimension. Let's say, suppose I do have an Excel. Okay, so here I still have an Excel. Here n mean equals to what? How many data I observe? I observe 100 data because that starts from 2, so the last number 101, so it's 100 data. And the p equal to what? How many dimensions does this x have? X has 2 dimension, as 2 dimension, no, 2 dimensions, so that my p equals to 2 and n equals to 100. So of course my n is bigger than p. But what if this happens, which is n is less than p? I know the very first reaction people may argue that no, it's impossible. How come you have more dimension of the data than you observe the data? Unfortunately, this is possible. Here I remember, I wrote, in some cases, it's very expensive to get the data, and hence it's possible because I don't have money. Simply, the budget is, it's not enough. While I have so many variables, features, to observe, but I don't have money to run a lot of experiments. A typical example is kind of biomedical science or pharmacy research. Pharmacy research, suppose I'm interested, for example, like a p parameters, but I need to combine the interactions of all of them. This will result in a p equal to 2. Sorry about this. Suppose I'm interested in q, okay, where q is the number of fundamental attributes. I'm interested in this q number of fundamental attributes, but because it's chemistry, chemical research, pharmacy or chemical research, all those kind of q fundamental attributes may tangle each other, so that I need to research on the interaction, and hence it's going to be 2 to the power of q. Say, for example, your q is equal to 10. 10 is a very, very small number. I mean, really small number. But 2 to the power of 10 is 1047, 1024, 1024, sorry, 1024. Think about it. How many medical those kind of experiments you need to do. The thing is, your budget is very limited, and it's possible, say, I only have money to do 10 times of the experiments, but the thing that the attributes that I'm interested in after combination gonna be 1024. You see what I mean? What you do? You cannot tell me, oh, because of this, so I can do nothing. No, I mean, we can actually still find a method to solve this issue. So this is why this is possible. And then we can actually give a very clear, super simple mathematical proof, actually. So basically, for, this is a mathematical fact. The proof is also very simple, just by the definition of the multiplication and the linear combination. Anyway, I'm gonna skip the mathematics, the details here, but because this is the fact, which is the multiplication will make your rank smaller and smaller. And then let me change the color. Let me change it to blue color. Then what we'll have, okay, so we'll have this. You just plug in, a equal to xt, b equal to x, so that I will less than this. And also because now I assume n here, I assume n is less than or equal to p minus 1. And hence I will have this. Therefore, for sure, this is not full rank. Why? Because for sure, let me use another color, let's say red color. For sure, this is not full rank. Why? Because think about this. Your XTX dimensional is this, but this one, the rank of XTX is less than n, is less than p minus 1. You see what I mean? In other words, it's a fixed that the rank of this one is less than p plus 1. In other words, what? This is not a full rank. So not full rank, then game over. How can you, like the very basic of the basic linear algebra, right? If something, a matrix X is invertible, it must be what? Full rank. And of course, it must be a square matrix, of course. But now I already proved it, it's not full rank, so game over. This is invalid. You even don't have this, I mean, this one even doesn't exist. What should I do? Of course, one method is use a pseudo kind of inverse, and you have several different types of pseudo inverse. And some other methods is something that we're gonna mention in this lecture, which is data reduction in linear regression. Basically, you will add a regularization factor, and then let's see how the magic, works. Okay, so this is one problem. Another issue is beta elements. Sometimes they can be very, very unbalanced. Unbalanced means something are extremely big, something are extremely small. Let's have an example. Now, suppose I solve an OLS estimator. Now, let's suppose n is bigger than p plus 1, okay? But suppose my solution is in this way. So you see what happens here. That 5.5, 100, 221 are okay, but this number, in terms of absolute value, this number is very, very small. Then immediately I'm gonna think, if it's very small, why do I need it? Why? Because think about this. What does this mean? This simply means y equals to 5.5 plus 100x1 plus minus 0.1 x2 plus 221 x3, right? Or let me make it more formal. Let me write it like this way. Here I, just ignore the multiplication here, okay? Just to make my life easier. So if you see this, what do you think? You're gonna think, hey, do I really need x2? Why? Because look at the contribution of x2 to the whole observation. It's so small, right? And I can make a more extreme case. What if it's like this way? You will probably say, hey, I really don't need your x2 at all. So if that's the case, why don't I just reduce the dimension of the x from 3D? Currently, I have three axes, x1, x2, x3. Remove it, make it to be like this way. Isn't it easier? True. That's one, again, this is just a fundamental idea. How in the real application, this may not be a good idea, but the idea, this may not be a good application, but the idea, fundamental idea itself is correct. Or consider another case, which is another extreme, which is the opposite. Here, you're gonna have a look here. This example, I have y equal to 5.5x, 5.5 plus 100x1 plus 10 to the power of 6 x2 plus 221 x3. So basically, you're gonna have this. Can I? Now zoom down to let me continue it. But okay, let me use another color and I have to rewrite it. Sorry. Y2 equal to 5.5 plus 100x1 plus 10 to the power of 6 x2 plus 221 x3. Okay. If you see something like this way, what's gonna happen? Do I really need to care about x1, x3? I don't care about these two, dimensions anymore. Why? Because x2 dominates. X2 really dominates, the whole prediction, because the coefficient is 10 to the power of 6, which is way bigger than 221 and 100 here. So if that case, can we simply just jump x1, x2 and only keep can we simply jump x1, x3 and simply keep x2 only? Can we do it? Again, the fundamental idea is correct, but in the real application, you may want to use some other methods like what we're going to mention here, ridge and lasso reduction. That's much more scientific. Okay, let me just clear everything here. How do you clear everything? Actually I don't know how to delete this. Let me see. No. How to clear all drawing. Oh, okay, now it's deleted. Okay, now let's see. What shall we do? And in general, the more parameter a model has, the more complicated the model is. So if possible, we always try to have a model with a small number of parameters for simplification. Of course, given that the prediction reduction, the prediction result is not too bad. You cannot like reduce, let's say, 10,000 parameters to one parameter and then make the prediction horrible, like this case, under fitting. You cannot make it this way, right? As long as we can make it similar to this, but the model parameter is smaller, I would like to do it. So that is the basic idea. So here we go, the idea of improvement, regularization. How can we solve these problems like overfitting? Or what if p is less than n is less than p, or something with extremely small or large absolute value? What shall I do? Okay, here we go, regularization, which is I try to use a method to kind of like balance balance the betas, or in some cases, if I can something like rescale or make a shrinkage of some parameters, I can try to push it to be 0, and hence I can tell you that, well, this one doesn't matter. Why? Because think about, let me just x y equal to, let's say, I just random put a number, okay? Let's say 10x1 plus, let's say, 12x2 plus, let's say, 0 x3. You're gonna immediately ask, so why do you need to write this 0 x3? Because because the coefficient is 0, I don't need it, right? Exactly. This is exactly the meaning that I want to find a scientific way to directly push you from, for example, let's say 0.01, I will push you to be 0. Of course, you need a scientific way, okay? The meaning is that actually when you push this one to be 0, these numbers could be smaller or bigger smaller as well. And sometimes this number is gonna be bigger to balance, the prediction. And this is the reason. But it's not you just simply only change this number. So that's the thing. This is called parameter shrinkage. And once I have some zeros here, simply I can drop the parameters. So this is the thing. First of all, this can reduce the risk of overfitting. Why? Because here I'm gonna reduce the number of parameters. With the small parameters exists, of course, the chances of overfitting will be smaller and smaller. And second thing is this will make the new number of features smaller. Again, go back to this example. Originally, I have x1, x2, and x3. Now, after shrinkage, suppose I make it to 0, 0 times x3. So of course, who cares about x3? I don't need to care x3 anymore. And hence, you see, I have a parameter reduction, number of parameter reduction from 3 dimension, the dimension equals to 3 to dimension equals to 2. The new number of features is smaller. A third thing, of course, is very clearly, I'm going to simplify the model. And fourth, in practical cases, what's the meaning of reducing a parameter or reducing a feature? Again, go back to the what chemical where it is. Here we go, like the biomedical or pharmacy research. Again, let's suppose original P equals to 10. You have 10 fundamental, chemicals to focus. Now, after doing something, you realize that, hey, you know what? Actually, I only need the chemicals of 1, 2, 3, and the 4 to 10, I don't need it. Imagine in your future experiments how much money you can save. You know what I mean? By dropping parameters in practical cases, that means a lot of saving in terms of no matter money or labor or whatever resources. So in most cases, reduction of parameters is very, very important and very, very welcome, in research or in science. And that's why if possible, we do want to find a correct way or a proper way to reduce the parameter. And that is how, or no, sorry, I should say that is why we need to do the regularization. Now we know why, but how? How can we do it properly? Okay. Regarding regularization in terms of mathematics, it's something that, in addition to the thing here, where it is, in addition to here, what I need to do is, so remember, I better open it. This is a linear regression for. So basically it is, give me 1 second. Okay, so it is this argument, this one, where's my, okay, anyway, looks like I didn't include it here. Let me write something here. What is that? Oh, anyway, activation. Okay, let me write it here. So basically I have had beta equal to argument beta I remember before they have the arg or maybe slash r. I'm not sure. Anyway, argument, let's say beta. But what I want to show is this. Let me see here we go. Y minus x beta norm 2. So this is the basic linear regression, the OSLR, ordinary least square linear regression. That's the thing. Okay. By regularization, what we want to do is where it is here. By regularization, what I want to do is like this way. I will, instead of add this one, I will add, sometimes use minus, it doesn't matter. Let me lambda, lambda, and then beta, and then let me for example, let me put k. So this k is just a parameter. So here I mentioned that on beta 0, beta 2, beta 1. So this is the meaning of the k. K equal to 0 or 1 or 2. So in other words, instead of minimizing this one, now I'm gonna minimizing the whole thing here. So first of all, some terms which is on beta 0, which is L0 regularization, and then beta 2. And later you will see this one is the best subset selection. Beta 2 is the rigid regression. Beta 1 is the most famous and a practical thing, which is the lasso regression. Okay, and then important thing is kind of like the sparse regression here, and that's the idea. So to estimate a beta with a smaller number, let's say suppose my previous parameter is t. Now I want to make a parameter to be t, where t is smaller than p plus 1. In other words, the other p plus 1 minus t parameters are set to be 0. This is exactly where this I erase it. Exactly this thing, which before I just wrote, for example, y equal to, for example, 1 plus 2x, 1 plus 3x3, 3x2 plus, let's say, 0 x3. So in this case, in other words, this one's eliminated. So that's a thing, and it's called sparse regression. The reason sparse is because I have those parameters to be gone. And the real application is that supposed to have 1,000 parameters. It could be possible that you finally only need 10 or 20 parameters, and most of those parameters are gone. It hence the name sparse regression. I try to make those zeros as many as possible under some proper mathematical settings. So that's the meaning. Okay, then let's see what do you mean by proper mathematical settings, right? Okay, so we're going to discuss 3 cases. Again, case number 0 is the best subset. Let's start from here. And okay, let me remove it. Okay, here we go. So first of all, what is the L0 norm? So L0 norm, using words super simple, just tell you, you give me a vector and then I'm gonna ask you, hey, how many non-zero numbers are there? Or if you, strictly mathematical, it's gonna be this way, where the indicator function delta AI means, how many AIs are non-zero, that's it. Maybe we just see an example, which is much easier. Say, suppose my A vector equal to this, -1, 10, 0, -5, 0, 10 to the power of -6, 0. I ask you what is the A zero norm, the zero norm of vector A. So we just count how many non-zero parameters, non-zero elements here. 1, 2, 3, 4. Be careful, although 10 to the power of -6 is a very small number, but it's not zero. So it's counted, okay? So -1, 10, -5, and 10 to the power of -6. And hence the zero norm of this vector A equal to 4. Simple, right? Very simple. Just you just count how many non-zero elements. Done. Okay. Yes, the definition of zero norm is simple, but this mathematical problem is extremely difficult. It's an MP hard. It's a bit too far. Maybe let me see. It's a very difficult problem. So basically, the mathematical formula is this. Still remember what is this one? Let me use the red color. Okay, give me a box. Hey Zoom, give me a box. Okay, the box here. So remember what is this one? This is nothing but the traditional linear regression, right? Okay. The difference is here. The difference is here. So let me this means subject to. That means I want to find a solution of beta not only to make this thing to be minimized, but also the beta must satisfy this condition using the language, using the definition of the zero norm. What does it mean? This means, okay, you can give me whatever the beta, but the number of non-zeros in this beta vector must be at most k. In other words, it's kind of like constraint, isn't it? Because before, my beta can be whatever. But here, I enforce your beta, the number of non-zero to be at most k. So think about this. Suppose my beta, the p, which is the dimension of the beta, excluding beta 0, okay? Suppose p is 10, plus your beta, plus your beta 0. So my total dimension of the beta vector is what? Is let's say 11. But now suppose I'm going to tell you, hey, you know what? You must give me a solution, which is the number of non-zeros of the beta is at most 6, let's say. Well, now I do have a concern. Why? Because before my beta hat, which is LS, what's the name? Least square, ordinary least square linear regression model. The beta 0 can be 10 because all elements are non-zero. But now enforce it to be less than or equal to k. So it's a constraint. And then how to do it. So technically, this is a linear regression with best subset selection. And it's proved that, again, I mean, the proof is in the paper. If you're interested, you can have a look at the paper. This problem is MP hard. Some of you may be not familiar with the meaning of MP hard. Using some simple language, it is NP hard is something we call it the God difficulty problem, which is non-deterministic polynomial time hardness. To the best of our knowledge, currently, if something is NP, that means it's difficult. But be careful, difficult doesn't mean there's no solution. I mean, in optimization, many mathematicians still use some tricks to solve some NP hard problems pretty well. But not for this one. Unfortunately, even p equal to 200, which is a very baby case in practice. In practical, this problem is almost impossible to solve. It's very, very, very difficult to be solved. So that's the thing. And one thing I do need to mention, which is the famous problem p equal to np is unsolved. The day before yesterday, I just saw a news which is someone invented. It was a GitHub kind of project, which is I forgot the name of the project, but the basic thing is that tool can help mathematicians to prove something, and it shows that some people try to use that software, that app, build a decision tree, proof decision tree, and then try to solve the problem p equal to np or not. And the conclusion is p is not equal to np. Nice. If p equal to np, the whole world collapse. Anyway, I mean, this thing can be, discussed hours of hours. But anyway, let me just give up here. But basically, if it's NP hard, that means in general, it's a very difficult problem to solve that I cannot tolerate when P is big. And hence, unfortunately, the idea of this one is very, very nice, but probably not practical. You cannot solve a large scale problem. And something, let me see, give me 1 second. Oh, by the way, there are some fast heuristic method, which are forward stepwise or backwise, backward stepwise selections are here. So let me show where you don't really have to click. So this is our course folder. It is in which lecture I'm talking about? Lecture 6, right? Okay, lecture 6. So these are the things about kind of like which I taught in another university many years ago. But these are actually PhD level courses. So here I showed a lot of theoretical results with strict mathematical proofs. Again, this is not required in this class because this class is a certificate class. I don't want to make it too difficult. But just in case if you're interested, you can get many theoretical answers. You may ask why that is true, why we have this, why we can make that conclusion. You can find many answers in those kind of extensive reading things. Okay, so now we have shown that it's NP hard and hence we cannot make it practical if P is too large. Then how to improve it? We cannot say because we cannot make it, so we completely give it up. And the truth is, yes, we can improve it. One improved method is to use L2 norm to replace the L0 norm. So L2 norm is the simplest thing, which is our world, the Euclidean norm, which is, the L2 norm of a given vector A. It's nothing, just a square summation of the squares and then square root. Say, suppose now A is 0, 3, 0, -4. So everybody knows 3, 4, 5. So the L2 norm of A, this vector is 5. How to okay, then how do you calculate it? 0 square plus 3 square plus 0 square plus -4 square, which is 25. And then square root of 25 equal to 5. So that's how you make it. I mean, this is the simplest thing. And then we use the parameter shrinkage based on this one. Remember what I just wrote? So basically, I'm gonna, instead of setting k equal to 1, equal to 0, which is subset, that's a subset problem. Now I make it k equal to 2. And this is the ridge regression. In other words, what I try to solve is this. Give me 1 second. Yeah, what I try to solve is this. Minimizing of everything subject to the two norm of beta of less than or equal to t. And in extensive reading, here I actually showed why these two things are equivalent. And so the truth is this problem, give me a box. Okay, this problem and this problem, the one I just wrote, and which problem, and this problem, they're equivalent. It is actually use something called like Lagrange dual problem. So, but again, I mean, it's not required in this course. Okay, so we can show these two are equivalent. And basically, so here's the thing. I can use the Lagrange form of the problem and write this problem. And it's easy to prove that these two problems are equivalent. And this is called ridge regression. And this problem is much easier to be solved. Why? Don't you feel one thing that everything quadratic, you see it? Everything with respect to beta is quadratic. And of course, we do have the interaction with the beta 0, beta 1, but it doesn't matter. It's still under the frame of the quadratic optimization problem. If it's a quadratic, it's convex. If it's convex, then it's super simple. We have tons of methods to solve it. I mean, I'm not going to show you the method, but really too many methods. So here we go. I want to show you a much more important thing, which is the geometric interpretation of the ridge regression. So we just show the algebra here. I know I want to solve this kind of optimization problem or method, algebraic mathematics. But what does a ruler mean? Can I have an intuitive graphical understanding of it? Yes, we can. And here's the okay, good. Here's the graphical understanding. Okay, so think about it. Suppose I have this is my beta hat OLS solution. Suppose, okay. And then I can always draw the contour plot, have the contour plot of the RSS. RSS is what? Let me see here. Where did I find the RSS? The square linear regression. The square sum of squares. Sorry, regression sum of squares. RSS. Yeah, regression sum of squares. RSS equal to what? Equals to this. So this is the RSS. Okay. Now, suppose this is the OLS, which is the true optimal solution, and then I have the contours of my RSSs. Okay, what does beta 2 norm is less than or equal to t mean? So here I assume I only have beta 1 and beta 2, 2 dimensions. This means beta 1 square plus beta 2 square are less than or equal to t, right? Yes, and then we know, I mean, everybody's learned, middle school. This is nothing but a circle, circle with the radius equals to t. This thing. Okay. So what does ridge regression mean? I want to find a beta such that make your RSS smaller, and meanwhile, your beta 2 norm should be less than or equal to t, right? So what I'm gonna do is this. Where is my Zoom? Give me a plot, please. Plot. Okay. Now I can let me use this color. So my contour is gonna be bigger. Sorry for my terrible plot. Bigger and bigger. But I cannot crazily increase until, you know what? Until I'm at this point. You know what I mean? Because of course you can ask me, so why do I need to stop here? Why don't I, for example, have something like this one, which is, for example, okay, RSS equals to, for example, let's say 150. Can I do that? Of course you can do. The problem is, what do you want to do? What do you want to have is to minimize this RSS. Since I here this point already, let me use another color, sorry, yellow color. Since this point already satisfies your constraint, which is beta 1 square plus beta 2 square is less than or equal to t. Why do I need to consider this green, contour in which RSS equal to 150? Because I want to minimize it. Understand what I mean? And hence, you see what I mean? Here, if I want to have, let me just clear everything. Too slow. Okay, if I want to have the ridge regression, the solution, I will always get something which is a tangent of this RSS contour versus my, circle here. And this is indeed the ridge regression point. And then you will immediately argue, say, hey, look at this. Here, my beta hat OLS is my true optimum, which is I don't have any constraints. In other words, the R square, the fitting result for sure is beta is at least as good as your beta ridge regression result. It can be even better. Why? Because think about it. A super simple logic. Think about this. Suppose I have, give me a box. Okay. Suppose I have this one, the optimization. Suppose I have wait. Suppose I have, let's say, beta hat equal to this, which is there's no constraint, only to minimize this one. And the second thing is beta ridge. This is beta ridge. Where let me write again. Okay, so this is beta hat ridge. Let me use beta R because it's very difficult to write. So let me ask you, which one will give a smaller RSS? Of course, it's going to be beta. Again, beta means there's no constraint, okay? Why? Because you don't have any constraints. Here for beta R, you need to constraint not only this one small, you also need to have the constraint here. So of course, my beta R will be worse. Give a bigger, worse means bigger RSS, bigger than or equal to, could be equal to, a bigger than or equal to RSS compared with the RSS given by beta, right? Yes. However, what's the point for me to use the ridge is that if you have a look at here, which is, okay, wait, sorry, let me use this color. Let me use red color. Okay, think about it. This is what? This height is beta 2 in my beta OLS, right? Okay. And similarly, this width is the beta 1 in my beta ORS, right? Okay. How about here? Consider the beta ridge. Didn't you see it's a shrinkage? My beta 1 ridge is smaller. So this one, the green color one, my beta 1 ridge is smaller compared with my beta 1 OLS. And similarly, my beta 2 ridge here is smaller than this beta 2 OLS. See it? And hence the meaning shrinkage. You see what I mean? Both beta 1 and beta 2 get shrinked. Both things get smaller. And you may ask again, so what's the point if I shrink this? Then imagine this. What if I have a beta k, which is super, super small? Let's say, suppose my beta k is something like beta k, let's say is equal to 0.1. Then after this scale of the shrinkage, it can be almost 0. You know what I mean? And hence I can kick it out. In other words, after ridge regression, the solution in your ridge regression, if I see something really, really small, close to 0, I may really directly consider to kick them out. So that's the point. And in the extensive reading here, if you read it, if X columns are orthonormal, the meaning of orthonormal means each columns, the dot product of them is 0, and the normal means the norm of each vector is not equal to 1. If that is the case, then I can even get your accurate shrinkage level, which is 1 over 1 plus lambda, where lambda is the regularization parameter here. So that's the thing. I believe section 1.2, I believe everything I've already proved there. If you're interested, I don't know which lecture where it is. Lecture 11, so it should be the second one. Yeah, in section the second one, lecture 11, 1.2. And here is the solution. And I believe basically if it's orthonormal, those things can be kind of like cancel each other. And then you directly have this kind of case. You just substitute the number inside, you can directly get this number. And but anyway, that's just a mathematical a result. But basic meaning is that because I have this kind of a norm, which is a circle, so I push it and then it's going to be convex and then everything is going to shrink. So this is the thing. Okay, so here's a interpretation of the ridge regression. And for the coding part, I believe I put it in the last several slides here. I will introduce the theory first. Okay, so we've already introduced the best subset problem, which is L0 norm. We've mentioned the ridge regression, which is L2 norm. And then the next one, which is the most powerful one, is the L1 norm. Again, first of all, I need to define what does L1 norm mean. L1 norm simply because is this, meaning the summation of all the absolute values of the elements. So again, let's make an example. Suppose A equal to this one. So this is a summation of all absolute value of the elements, which means 0 plus 3 plus 0 plus 4. Be careful because absolute value, and hence -4 becomes 4. Finally, 3 plus 4 equal to 7. So the one norm of A equal to 7. So that's, it's very simple. And then for L1 regression, the regularization, the same thing. You can see, the only thing we are changing here is the norm here. You see what I mean? No matter 0 regularization or 2, which is ridge regression, regularization, or 1 regularization, everything the same except for the norm here. So you may ask me, so by the way, also I can write the equivalent to Lagrange form, which is here. And again, in the 2 norm, I have square, 1 norm, I have absolute value. Why? Because it's by the definition of the norms. You might say, okay, great. It's called a Lasso regression. Everything looks good, but what's the point? What's the difference? You have different norms. Okay. Again, first of all, I can show, I believe I showed you here, which is the Rebus proof of the meaning algebraically. But I personally would prefer a very intuitive geometric interpretation. You will see just by changing the norm how powerful it is. Okay, similar thing, I plot the contour. Again, I suppose this is a true OL solution, and I, plot the contour, blah, 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 here. And then here we go. Similar idea. You can basically, give me a plot. Okay. You can basically make it even bigger, bigger and bigger. Say, suppose this is R, S equal to, let's say, for example, okay, 60. You can do, but I don't have to do. Why? Because I want to have the minimized RSS. Since here, this point satisfied beta 1, beta 0 less than or equal to t, and this point is equal to the RSS is 36. Why do I need to increase the control and get a worse solution, right? So that's the thing. Okay, now we can see that this indeed is the beta Lasso solution here because I have the minimum RSS, and meanwhile I satisfy the constraint, which is beta 1, the beta 1 norm equal to t. Beta 1 norm here is 2-dimension. By definition of the 1 norm, it's beta 1 absolute value plus beta 2 absolute value less than or equal to t. By the way, does everybody know why this one has this shape? I mean, you only need like the knowledge of middle school. I believe you just, you just think a little bit, consider four cases, which is beta 1, beta 0, both greater than 0, then beta 1 greater than 0, beta 2 less than 0, beta 1 greater than less than 0, beta 2 greater than 0, and beta 1, beta 2 both less than 0. Four cases, you can easily plot it. And indeed, this is the truth. I mean, this one, sorry, where it is. This one, the geometric shape is this, okay? And hence, this is the first one that I'm gonna, match with the smallest RSS mean while satisfy this condition, and hence here. Again, you may ask me, so what's the point? The point is here. Let me ask you, first of all, for beta 1, isn't it smaller? So for beta 1, so in my original OLS, the beta 1's here. And then in my beta lasso one, the lasso solution beta 1's here. So indeed it's shrinkage. And the most significant point is here, is in beta 2. Because in beta 2, it's not only a shrinkage, but a vanish. Why? Because think about it. In my lasso solution, beta 2 is 0. That means what? That means I don't need this beta 2 parameter anymore. And hence I reduce the two-dimensional data X to be one-dimensional data. So this is a big improvement. You see what I mean? And you may, if you want to think a bit further, why this is going to happen, but why in the ridge regression, this is, I mean, technically it can happen, but almost impossible, because unless, your eclipse here is, kind of like this, and you happen to meet this point. Otherwise, it's almost impossible. It's just, practically it's impossible. Theoretically, it's possible. However, for the lasso regression here, this is very common. I mean, later we'll see. I mean, in many practical cases, you're gonna really attain some parameter equal to 0. It's completely vanished. So this is a big point. If you want to ask why lasso gonna be vanished, but ridge cannot get vanished because of the shape. Because let me see here. Plot a circle, give me, okay, because of this. So it's not too good, but it's Zoom's fault, not my fault, Okay, because see it, if I have a circle, which is the shape, the domain, the feasible region of the ridge, it's gonna be like this way, so that usually your tangent point is gonna be somewhere here. It's gonna be, something like this. That's gonna be your tangent point. However, if I have the lasso regression has the corners, see it? It's a diamond. With the corners, you're gonna have much higher chance to hit the corner. Why? Because it's very difficult, unless your shape, let me plot, give me a plot. Unless your shape is kind of like, sorry, it's just very difficult to plot, kind of like this one, you know what I mean? Then your tangent point is going to be here. But this is very rare because, your long, oops, sorry. Because how to make it? In order to make it, your axis must be parallel, must be like this way, parallel to this shape. But this in practical is very difficult. And hence, if this one does not match, then what? Then you're going to have something, very possible you're going to have something like this way, or sometimes here, or sometimes even here. That's the reason why a diamond, shape here, you'll get a much higher chance to reduce the parameters. Of course, here's only 2D. I mean, supposing a much higher dimensional, data, you can have many points to be shrunk to be 0 and hence vanish. So that's the meaning of the lasso L1 shape regression. It has a feature selection, a real feature selection. It's not like from the ridge. The feature selection is a roughly because you see the beta from beta ridge 2 is very small. So you manually, you roughly kind of like remove it. Here, lasso is not a roughly remove it, but a real removal. You know what I mean? It will really make this one to be 0, and hence beta 1 is not needed. And hence that I reduce the dimension of the data from 2D to 1D. This is really no kidding. And fundamentally why? Because of the shape, because I have a diamond shape versus a circle shape. It looks a small step in terms of the geometry, but it's a bigger step in history of statistics. Because of this invention, I believe the author got the highest award, Tibershani, in statistics. And it is considered as one of the, I believe not one of, but the biggest result, the best result in 1996, in the whole 1990s, even the whole 20th century. So this is a milestone solution. Lots of regression. But anyway, some rigorous proof, algebraic proof. If you are interested, you can see something like this. And then in some cases, it can be a really big reduction from, for example, from 1,000 dimension to 30 dimension. It's, that's the thing. And if you're interested in the original paper, how it was discovered, you can read it. You just search Robert Tibershani and the lasso regression. You can find the milestone paper. It's really a milestone result. Anyway. Okay, so this is the lasso regression. So here is a comparison of the ridge regression versus the lasso regression. Ridge regression have the shrinkage, but it doesn't have the parameter selection or variable selection. By comparison, lasso, it's not only parameter shrinkage, but also the variable or parameter selection. So that's the thing. However, a good thing is that for ridge regression, it's super fast to solve it. And the solution is an analytical solution. By lasso regression, it's usually a closed, numerical solution. It is kind of like subgradient method, least angle regression methods. These are fast iterative methods, but they are not the analytical method. So this is a comparison. Okay, so here we've already mentioned, first of all, why do we need to have the regularization? Then we introduce the 3 types of regularization, L0, L2, and L1, corresponding to best subset selection, ridge regression, and the lasso regression, and then the geometric meaning of this. Regarding the solution, again, I'm not going to show, the stepwise solution here, iterative solution here. Everything, has already been coded. Okay, and then the next question is, in both lasso and the ridge regression, I have the lambda here, where the lambda is called the regularization parameter. How can I choose the lambda? The only thing I know is lambda is bigger than 0. That's it. So what is the number? Should it equal to 1, 10, 100, or 1,000? How can I choose a proper lambda? So this is the issue. In general, it is something called how to choose a hyperparameter. So for example, this lambda here in ridge and lasso regression, it is a hyperparameter, which hyperparameter means it's gonna be tuned, when you're gonna tuning the model instead of directly be fit in the model. So we usually have several methods. One of the most popular method is called cross-validation. Again, there are some cross-validation methods here. We're going to focus on the k-fold cross-validation. And another super popular method is what the bootstrap, which is, you kind of like you make a random choice, and then you put the sample back without putting the sample back, and then you make a choice again. So that's the bootstrap. But that's another thing. Usually it's very widely used in deep learning. But here, to make my life easier, I'm gonna show the k-fold cross-validation. So here are the ideas or the steps. So the k-fold cross-validation is, first of all, we are gonna partition the observed data, including, be careful, both training and the validation data. Here, by the way, one thing I do need to mention here is I do not discuss the test data here. Everything when I say the regular the cross-validation is in terms of the training data and or validation data. Okay, so here for both training and the validation data, I partition all those kind of observed data into k equal sized groups. We call it subsamples, and then we retain the first group to be the validation data, the data set, and then the other k-1 as the training data to train the model. Then after training the model, we'll calculate the metric. Here we use the metric as MSEE, mean square error. We will have the definition here later, based on the validation data. And then we just set the second group to be the validation data, and the other k-1 group to be the training data. train it, calculate the MSE, then the third group to be validation, until the last kth group to be validation. And finally, we compare all those metrics and choose the lambda, which gives the smallest error or the smallest this metric, let's say MSE. And then we choose that lambda to be the lambda of the whole model. I know you may get a bit confused here. No worry. Let me finish this, and I will show you, graphic example here. And then, by the notations, suppose I have t lambdas to consider, lambda 1 to lambda t. Then for each lambda j, we are gonna use the k-fold cross validation and using MSE, for example, as a metric. Then I'm gonna choose the j with the one give me the smallest MSE, and then I will choose that lambda j. So that's what I'm going to do. Let me again, before I show the example, two things I want to mention. Thing number one is that we only need to partition for one time, for once. You are not partition for many times, because this will make a comparison unfair. And second thing is, in addition to the cross validation, there are many other methods for the lasso regression to tune the parameter. The two most well-known probably are AIC and BIC. I mean, again, I don't have the time here, but you can, if you're interested, you can click this for the Wikipedia. It shows you step by step. Okay, now let's show an example. How do we really do the k-fold cross validation? Suppose here I'm interested in three lambdas, lambda equal to 1, lambda equal to 1.5, and lambda equal to 2. I want to choose the best one, but I don't know which one should I choose. Okay, now suppose I have 8 observed data, and I set k equal to 2. Okay, now we will have k equal to 2 means two groups. So 8 divided by 2 equal to 4. In other words, I should have 4 data for validation and 4 data for training. So first I consider the first lambda, which is lambda equal to 1. Okay, now, so this is data 1 to data 8, the 8 data. First of all, I will randomly partition the data. Random partition means I just make a random order. It's not gonna be, the order for 1, 2, 3, 4, 5 until 8. It's gonna be, for example, I random make the order to be 4, 3, 8, 1, 7, 6, 2, 5. Okay. Now remember, I have two groups. Each group has 4 data. So I'm gonna choose the first group to be the training data in green color, the second group to be validation data in blue color. So green, blue. Okay, here we go. Then I'm going to train the model based on the training data, which is D4, D3, D8, and D1, and then calculate the MSE 1, 1. The first one means for the lambda 1. The second one means it's the first trial, say it's MSE 1, 1. You will have MSE 1, 2 later, where 1, 2 here. Okay, so here I get MSE 1, 1, right? Okay, now I cross validation. That's the meaning of cross. That's the reason why the method is called cross validation. Cross validation means I'm going to make the green data here to be the validation data, and meanwhile make this blue validation data this time to be the training data. And here you see I cross it, this one to be validation, this one to be training, which is here. Okay, now I train the data based on D4, sorry, D7, D6, D2, D5 again, and then I calculate the MSE based on the training the training data. So I get MSE 1, 2. Okay, now I'm gonna have what? The MSE1, meaning that the MSE for the whole lambda equal to 1 is a half because I only have MSE 1, 2, 1, 1, and 1, 2. If you have 1, 1, 1, 2, 1, 3, 1, 4, then 1/4 of it. But here, since I only have 2 groups, so it's going to be 1/2 of this one, meaning the mean of these two MSEs. Now I get MSE 1. Okay, now for lambda equal to 1.5 and lambda equal to 2, I can do the same thing. And then I get MSE2 and MSE3. Now I just need to compare MSE1 versus MSE2 versus MSE3. Which one is the smallest one? I'm going to choose that lambda to be the lambda here. So this is the cross validation. One thing I do need to mention, be very, very careful that using the same data partition, okay? You use the lambda 1 for this data partition, which is, for example, this order D4, D3, D8, D1, D7, D6, D2, D5, and then first group here, second group here. So for your lambda 2 and lambda 3, you should follow the same order. You should do the same thing. You cannot say, okay, I calculate lambda 2, I use another order. For example, D3, D4, D1, D8, D6, D7, D5, D2. No, then the comparison is going to be biased. You know what I mean? The whole cross-validation, you will partition the data for only one time. So that's the thing. And also I realize I forgot to mention, sorry about here. I forgot to mention the MSE. So MSE, the mean is mean squared error. It is this one. And you can actually see the RSS is that part. So in other words, the MSE is nothing but 1 over n of RSS, where n is the number of observed data. So in other words, it's just, in terms of the data, average MSE, the number of the data average, average RSS. Okay, so let me show you a bigger example, which is suppose here again, I'm interested in lambda 1 equal to 1, lambda 2 equal to 1.5, lambda 3 equal to 2. And then I have 12 observed data, D1 to D12. Exclude, again, when I say observed data, that means I'm going to use these things for training and for validation. Okay, now I have K equal to, suppose my K equal to 3. So 12 by 3 equal to 4. And hence, again, each group includes 4 data. So I always have one group of validation and all other groups are training data. Okay, now suppose, I choose again the last group to be validation data, the first 2 groups to be the training data. Okay, now validation data, training data. I train the model based on the training data. In other words, the first 8 data. Again, here you're gonna randomly, you're gonna randomly generate an order. It's not gonna be really like following the order from D1 to D12. No, it's gonna, for example, here I randomly, generate the label and I get a D5, D10, D5, blah, blah, till D8. So this is my order. Again, the first 2 groups are gonna be the training data, while the last group gonna be the validation data. Now, excuse me, let me drink some water. Sorry about it. Okay. Now, you are going to train the data based on the training data, which is the first 8 data, and then you are going to calculate the MSE11. Okay. Now, cross-validation means you're going to choose the second group of the data to be the validation data, and the first and the third group of the data to be the training data. Okay. Again, based on your training data, you calculate the MSE, and then you're going to have MSE12. The third time, again, cross-validation, you're going to have this group, the first group to be the validation data, and the second and the third group to be the training data. And you see the part of the blue color or the validation data. Last group, second group, first group, you see, cross-validation. And then you train the data based on these and then calculate the MCE13. Okay, now get the mean of the MCE, because you have 3, K equal to 3 groups of the data. So your MSE1 equal to 1/3 of the MSE11 plus MSE12 plus MSE13. So this is MSE1. Similarly, for lambda equal to 1.5, you have MSE2. For lambda 3 equal to 2, you have MSE3. So now you have MSE1, 2, 3. Then you're going to compare. You choose which one is the minimum. You will choose that lambda. So that's the meaning. Clear. So, okay, now after these 2 examples, now you go back to the steps here. It's going to be easier. You first of all, you retain one group, say the last group as the validation data, and the other groups to be the training data. Calculate the MSE, the metric, let's say MSE here, based on the validation data. Then cross-validation, which is you set up the I minus 1th group of the data to be a validation data. Calculate the MSE, cross-validate I equal to I minus 2 until every group of the data is selected to be the validation group, validation data. And then you calculate the mean of this metric. And then this single value, like the MSE1, will be the metric of the current hyperparameter for lambda 1. So this meaning, okay? Say your MSE1 here going to be the metric for your lambda 1. MSE2 for lambda 2, MSE3 for lambda 3. And then finally you choose the minimum one. Done. Whew. Okay. Now I can go to the coding stage. Okay, so the coding stage is what? Okay, so first of all, I'm gonna have a look at this group of the data. I can show the data here. Where what Oh, sorry. This is lecture 6. That's why I'm thinking why I don't have the data. Okay, let me first of all show you this group of data, which is 6-dimensional data. You have y, and then you have x1 to x6. Okay, now let's see how can we do it. Sorry about it. Let me have review myself here. Okay, so I believe basically I modify the data by the class, but here, to make the final result, consistent with my lectures, I fix it. Remember, before usually what we do is we'll have x train, y train, x train, x test, y train, y test equal to split. Give me 1 second. Linear function split, and then test size equal to 0.3 or whatever the 0 point something. So what I'm saying in this column here, X train, X test, Y train, Y test equal to secondary model selection, X, whatever train test split, X, Y test size. So practically we should do like this way. But here, please excuse me to set up in this way. First of all, I admit it's unfair, but again, I make the first, I specify the first 70 data to be my training data, and the last 30 data to be my test data, because totally there are 100 data. I mean 100, sorry, not this one. I can close this one. Totally 100 observations. The number starts from 2, so it's 100 observations. The reason to fix this one instead of making a randomized selection is because I want to, make the result consistent. Okay, and now I define it. The thing is, this is for, okay, let me just code it. To make my life easier, sometimes to code it is better than directly to show it here. Okay, so let me open the notebook where it is here. So I can have my lecture 6 here. Lecture 6, come on. Lecture 6. Lecture 6, linear regression 2. Huh? Why? Oh, okay. I cannot have the column. Lecture 6, linear regression 2. Okay. Now to save my life, I'm gonna cheat again. Sorry about it. So I'm gonna remember my class. I don't need a plot, however, so I can directly apply from here. Let me just copy and paste here. And then I can have where it is. Actually, I even don't need this. Let me see. Oh, okay. I can directly get it from the lecture 4, which I believe, if I remember correctly, I should have a class in the final. What is that one for? Why don't I have a class? Okay, anyway. So in that case, I will have to choose from lecture 5. Sorry about it. Lecture 5 class. The first time that I use the class for linear regression. No, yeah, this is the one. So let me just copy and paste everything. Copy and paste here. Okay, here we go. So I have the second learn. I have the what? Linear regression here. Okay, now I can do the things here. So first of all, I will have let me make it to be linear regression comparison. Let's say linear regression compare. So first initialization is the same thing. Oh, by the way, I need to change the thing here to be, let me see, lecture number 6. Okay, let me first, because otherwise I will forget. I'm sure I will forget it. And lecture 2 linear regression example. What's the name of the file? 60. Okay, so I just need to make it to be 60, and also I need to change this one as well. Otherwise I'll forget for sure again. Okay, compare. Okay, here we go. And I don't need to plot it anymore. I can remove it. Okay, and then I can make it to be, let's say, lecture 6, LR6. Okay, so first of all, which is basically setting the initialization functions, blah, blah, here. And then I'm not gonna, as I mentioned, I'm not gonna make it this one. I'm gonna just cheat it to make my result consistent. So, and hence I have self.x.train, self.xtrain equal to self.x, and then the first 70 data, self excuse me, self y train equal to self dot y 70th data, and then self dot x test, self dot x the last 30 data, and self dot y trained y test, sorry, y test equal to self dot y next 30 column. Okay, so this means I'm gonna set up all the data, and here I'm not gonna okay, so here first of all I don't need a plot anymore, so that I will have here the model. So I will define the let's say let me use else LR first. Yeah, I give me 1 second. Sorry about it. I believe yes, define LSL first. Define LSLR self. So this is the LSLR model fitting. Before that, just let me do one thing. I just wanna make sure my initialization function, there's no problem here. Let me just run it. Okay, it didn't show error. That means everything's correct. Okay, now I can define this one. Okay, self.model equal to, no, I don't need self.model anymore. Let me make my life easier. Let me just call it linear regression LR equals linear model dot regression and then here I don't need the self at all. Again, the reason people may ask, so why sometimes you need to use self sometimes, let's say here, why don't you use self, dot LR instead of using LR? The reason because I don't need to kind of like cite, or I don't use LR anymore. You know what I mean? It's kind of for me, it's kind of like an intermediate variable. I don't want to save it anymore, so that I can use LR. Of course, if you say, in case you really want to save it and use it, later, let's say, suppose after LR6, you say LR6.LR. Can I do it? Yes. Then you want to make it to be self.LR. Here, I just, because I know in this specific example, I know that I want, use LR6.LR. That's why I just, to save my life, I directly use LR. Okay. So here, again, similar for R2, because everything I will print it, I will print everything here. So I don't need to use it again. This one equal to, let me see, self.model. No, it's gonna be LR dot model dot score. Let me see. No, I don't need a model even, because LR dot score and the self-train, y train. Okay, now I will have the y predict. Where's my y predict here? I will have, give me 1 second. And I don't need this one. Okay, so now again, LR predicts self dot x text correct. Then I'm gonna print the R square coefficient, of linear regression is R2, and this one. Okay, and then I'm gonna print the intersection LR dot coefficient self dot x dot shape or LR dot coefficient dot efficient. And now I need to, let me see. Sorry, I forgot. What did I do here? Train coefficient. Okay. So okay, I need to get the mean square. I need to get the mean square error. And okay, here we go. But if that case, I need to include something as well here. I will need to from scikit-learn dot metrics, I believe. Yeah, dot metrics import or to mean something, means square. Oh, here we go, mean squared error. Okay, so now what are we excuse me, what we're gonna do is here I'm gonna print the beta coefficient is here. Now I'm gonna print the what, the MAC, the mean square error on the test and the training data. Okay, So now I can print, first of all, because I've already have X train, Y train, sorry, X test, Y test, and hence I can have print the MSE on the past data is, let me see, mean square error. Let me see, does it have the, oh, does it have the help? Okay, here we go. I press shift and the table so that you can see the help here. Args here and the field, no, let me see, stop the values, wait. No, it should be two Y's. I should only need a two Y's. 1 second. Yeah, because I have the Y test already, and then I can have the Y predict because I already calculated all the Y predict. Okay, so here I already get the Y predict, and then I can define something like the accuracy from .3f. And now I have what I have this, which is for the MSE of the test data. And here I believe I did for the training data as well. This is for the training data. Okay. And then I can, let me see. I don't need this anymore. On the training data itself, dot Y training. And then, oh, wait, 1 minute. Here's something wrong. Wait. Here, Y predict is, okay. So we need one more step here. Sorry about it. We cannot print it because we do not have the Y predict for the training data. Y predict training equals to let me see, LR dot predict. And then so here's rather simple. So here we put the test data here. So you just simply need to put the X train there and done. Okay, so X train there is here. Now I should be able to put it here. Yeah. Y predict training. Okay, here we go. And then let me just, in case I'm wrong, let me just run it. LR6 dot LSLR. Let me see whether it can be. Oh, great. My model. That's the thing. The reason I want to write in this way, to be honest with you, is because I want to copy and paste so that I will always use those things. You know what I mean? For what Ridge and Lasso. So just because I want to be lazy. Okay, great. So looks like it's correct. The MSE the test data is 101, and the not test data, training data is 78 point whatever the number. And let me just make sure that my conclusion. Let me close this one. My conclusion is correct. So it should be about uh what did I? Here. That's why. It's yes. Interception. Let me just compare the result. Oh, 744, 75. Oh, maybe because of three. Okay, I can make it to be 3F. I just want to make it the same to be my slides. 3F, and here this is 2.69, 101, 53, 78, 4045. Okay, everything's good. Okay, now I'm gonna code for the lasso and the ridge. Ridge and lasso, let's say. Okay, now I'm gonna, oops, sorry. Okay. Uh, in addition to this one, I'm just copy and paste something, and then I can be kind of like pretty lazy. The lasso, a ridge fitting. Okay, so now I'm gonna not LR. I'm gonna call it, let's say ridge R. I can call it. No, let me call it ridge R. Otherwise, so many R's, I will get very confused. Okay, so I'm gonna copy and paste. Ridge R equal to, be careful here. It's not gonna be a linear model dot linear regression anymore. It's gonna be ridge. Okay, it's gonna be ridge CV. And remember, in the ridge regression, you have what? You have this. You have the lambda. You have the regularization parameter lambda here. And in scikit-learn, interesting thing is they call it alpha instead of lambda. You can see alpha is equal to this. So this shows you how you would like to choose your alpha. But here by the way, here you cannot call it lambda because that's the keyword. It's defined to be alpha, you know what I mean? But you can make the number whatever the number. Let's see what did I use here? Well, okay, 1, 3, 10, 20, 3, 5, 10, 20. 1, 3, 5, 5, 10, 20. Okay, this tells me the alpha is this one, and then you just replace L alpha range. So here I'm not gonna use control F or something. I'm gonna try to make it, just in case I make any mistakes. LR is gonna be range. Oh, here is very important. Ridge regression is this one, and then here's ridge dot interception, and then here F self, F, and a ridge coefficient, and then here's gonna be let me see. Okay, looks here is correct. Let me do here again. LR6 dot ridge. Okay, great. Ridge is wait, why what is wrong? What? Wait, alphas. Sorry about that. Alphas. Okay. Still wrong? Ah, forgot. LR. Ridge. Okay, here we go. Okay, let me just make it this. So I can put slash n. So slash n means change the line. So it's gonna have a blank line in the middle to make it more beautiful. So that you can see first of all by comparing the what the coefficients here, you can actually see a shrinkage. You see what I mean? It is indeed a shrinkage. Like, I mean, shrinkage, what I mean is in terms of the absolute value. You see, this number is bigger than this number. This is bigger than this. Everything is shrinkage. Second thing is, unfortunately, we do not have anything close to zero that I can direct shrinkage to be zero in this specific example. No worry, Lasso will. I remember Lasso made one number to be zero. Yeah, so first of all, let me just do some cheating. I'll just want to make sure that my numbers are correct. Yes, correct. Okay. Now we do the lasso. Then it's going to be easier. That's the reason why I want to make it into this structure and then write everything to function in the class. Okay, now here's going to be a lasso. Lasso model, and then I'm going to make it to be lasso R, meaning lasso regression. Lasso. Okay. I hope I'm not gonna miss something here. Here's not gonna be ridge regression anymore. It's gonna be lasso CV. Okay, I remember I still have alphas. Okay, I will remember this is alphas. Yes. Okay, now I use the same parameters. I believe. Let me see whether I'll say where it is. 1, 3, 4, 10. Okay, yeah, the same thing. Okay, and then I'm gonna have everything to be lasso R instead of ridge R, lasso R. Lasso regression here, and then it's gonna be the lasso R. Uh, lasso. And then what else do I still have ridge R's here? Looks no. And one more thing is here, lasso R. Let me see on the training lineage. Okay, maybe we can do it. Okay, great. So this time, and you see the results here. Did you see a 0 here? And in other words, you know what? Indeed, we shrink x 3 to be 0. In other words, here's 6-dimensional. Now it's only 5-dimensional. The x0 is gone. But by the way, can you interpret the meaning of here? Let me write some here. So this simply means what? Oh, sorry. I'm talking about lasso, okay? I'm talking about this one. This simply means first coefficient negative 3.312. 312. So what I'm saying is here. What I'm saying is this number. This is beta 0. And then beta 1, beta 2, beta 3, beta 4, beta 5, beta 6. Let me continue. Wait. I cannot write anymore. Anyway, Zoom. Sorry about it. Let me just rewrite. Let me just rewrite everything here. Let me insert something here. So That means y equal to the color. Let me use, let's say red color. Y equal to negative 3.312 plus 3.11 x1 plus 1.700 x2 minus 0 x3 plus 2.622 x4 minus 4.887 x5, and then what else? The number I cannot see it. Minus 6.074 x6. So that's the meaning. I don't know how to make it bigger. Yeah. This is for the lasso regression. I mean, for rich errors, the same. Okay, that's how can you interpret it. And also you have what? You have this. The MSE on the test data is this one, and the training data is this one. And then, ironically, the test data MSE is even better than the training data MSE, and then coefficient. Okay, now we can go back. This I hope the same thing as my oh. Okay, yeah, the same thing, but looks like I forgot one thing, which is the lambda selected. Yes, I need to select the lambda. The cross lambda. Oh, it's alpha R. So sorry about it. I can just add here. So well, where's my here I have the muscle right brained. So I will have us here and here I don't need a slash n. So I can say, let's say the alpha selected, the lambda not alpha, lambda selected via cross validation is rich R dot alpha, yeah, alpha this. And similar thing here from the paste. Okay, here we go. And yes, in this case, both Ridge and Lasso select one. I can clear the drawing here. Both Ridge and Lasso, sorry, both Ridge and Lasso select one to be the K, to be the lambda. Remember, our lambdas are selected are here. This is our lambda selection. See it? We're gonna select the best lambda from 1, 3, 5, 10, 20. And this is exactly the same as what you mentioned, like here. You know, the difference is here I have 1.52, and here I have 1, 3, 5, 10, 20. So that's the thing. And finally, using cross validation, both of them are 1. And then here are the results. And the most interesting thing is here, negative 0. I mean, positive and negative, not a big deal. So indeed, it shrinks. So Lasso shrinks had the feature selection, which is beta 1, beta 2, beta 4, 5, 6. Ignore beta 3. And also shrinkage, because if you compare, the parameters, indeed, all of them are smaller. Shrinkage. For Lasso, for Ridge, there's no selection, but still shrinkage. So in general, Lasso is better, will give you a better solution, but Lasso is more difficult to compute. Here we only have 6 dimension. If you have, let's say, many million billion dimensional, Lasso computation will be much slower than Ridge computation. Okay, I don't think I have time to run the next example, which is P equal to 10,000 meter, 10,000 parameter, 10,000 features, and equal to 10,000, and totally you will have 1 million. Into 1,000, sorry. So totally you will have 10 million, not 1 million, 10 million observations. And then you will see something interesting, I believe. I can show it now without coding. So we originally has 10,000, sorry, 10,000 parameters in which the first 400 features are binary features, means yes or no, 1 or 0. But finally, by Lasso, we only have 572 non-zero betas. In other words, there's a shrinkage of or feature reduction of 94.73%. Think about it, how big it is. right? We only need to use 527 among 10,000 original features. That's a huge data should I say dimensional reduction or feature selection. Okay, I will stop the lecture here. In the next class, I will run this example, and then we'll start our classification, which is the k-nearest neighborhood. Thank you very much, and have a good night. Bye-bye.